is the process synchronization. As we have seen the last week, the old-fashioned operating system, some of the old-fashioned operating system can create only one job, which means one process at a time. Like, for example, the MS-DOS, MS-DOS. I'm not sure how many of you have the experience of using the MS-DOS or the MS-DOS, but when you run the program using the MS-DOS, you can run only one process at a time, one program at a time. Okay? However, nowadays, most of the operating systems support cooperative the process, which means when you execute the job, so using the multitasking, so multiple processes are working together. However, when we are using the multiple process in operating system, there might be some problems. For example, think about we have bulletin board. So we have the bulletin board. It's number 0 currently. There is a student A and another student B. This student always increase the value by 1, like the increment, what is the instruction in assembly language? It's a +1 usually. This student usually -1. Okay. At the same time, so I let both the students do their job regarding to such a bulletin board. What will be the output after one execution of their job? 0? 0. Which means +1 and -1. Okay? What else? Both first student A read the data, right now it's a 0. And also student B read the data, it's a 0. It's just before student A update the data. Then +1 is going to be 1. Then write the data. So this is going to be 1. Then this one is -1. Then update is going to be -1. Right? That makes sense.
1 minus 1.
Yeah, so first it was a 0.
Yeah.
Then both students read the data. So it's a 0 and 0, right? Then student A, he did his job because +1. So it's a 1. Then update it. So it's going to be 1. And student B, after that, did his job. So it's a -1. Then update it. It's going to be -1.
When both are doing the job at the same time?
It's not possible because when you write something, can other student write the data? Okay? So it may be -1. Also, similarly, if student B update the bulletin board -1 and take down by the student A, then student A write his data +1. So it can be +1. So -1 or 0 or 1. This usually happens. Yes?
Why not 2?
What about 2? Is it possible to? How?
I mean, the student A also change the value of
It starts from 0.
Yeah.
Yeah, then only one time execution. Okay, only one time. Then 2 may not be possible. But anyway, the key point is we cannot guarantee the output.
I mean, is the space is shared for student A and student 2?
Yeah, they are sharing the data. That's a cooperative processing. So we need to, so in the project, okay, if that is a group project, you guys need to share the other guys' work. If you do not share the output or data, you cannot complete your project. So this is a cooperative job. So they are sharing the data, but the problem, sometimes we cannot guarantee the output. Okay, that's called the synchronization problem. So synchronization problem is always a big issue in any computing the system. What about the database? Database is more critical. So when you create a database, how many databases? It's only one database. Then how many applications? You have multiple applications, multiple users, multiple transactions. They try to access the same data. So it's always happen. Such a non-guaranteed, it's a conflict situation. So you guys need to address that problem. Operating systems definitely need to address such a problem. So that is called the process synchronization. So synchronizing means we guarantee the data. Okay. So how can we guarantee the data? So basic idea is what? Lock. Okay. However, problem is different types of locking. Okay. So we are going to learn basically using software, using operating system, using hardware. So we are going to use the different the locking mechanism. Even using the software program, using your own algorithm, we can solve the problem of the synchronization. But most of them are based on the locking, which means simply we give the key. So when a student need to access this bulletin board, one of them need to get the key. Okay. So but this key cannot be shareable. Right? So think about when you go to the bathroom, to go to the bathroom, you need a key. Are you going to share the key? You don't know, right? It's the same thing. So why student A access this data, first get the key, then update it. So it will be the 1, okay? Then the student B can access this data, then read the data is 1, then -1, it will be 0. You can guarantee the output. So sequentially, it will be processed. But what types of key? There are a bunch of different keys. There are different locking mechanisms. We will discuss about such a basic locking mechanism, basic synchronization problem solution in this chapter. Okay. So this is called the race condition. Race condition means when multiple process. If you have only one process, one student, we don't need such a synchronization issue or the key or locking. Okay? Whenever this student wants to access, he can do that. But in case we have several processes, then if they need to access the shared data, especially write the data. If they want to only read the data, there's no problem on the race condition. Because they just read, it's a read only. You don't need a lock, you don't need any synchronization issue. However, in case you have to write the shared data, then it's called the race condition. In case of race condition, but some of the different textbook use a different name of such a condition. In this textbook, we use a race condition, but the other used, for example, conflict situation. So conflict is the same name. Conflict, the same name of the race condition. In case of the race condition, we need to prevent such a race condition. So that is a synchronization issues. Okay, so we are going to use the very popular, very well-known producer-consumer. The process, the producer usually create the data, write the data, and the consumer, they read the data from the buffer. So this is an example of the one, in details of this problem. So let's consider student A is one process, and the student B is another process, so two processes. So to increase the data by 1, we can actually use the instructions. Okay, one is read the data from register, the data from the shared data to the register, move, and also increment and move. from the register to the shared data, the memory. Okay, similarly, the student B is minus the 1, so we can use the decrement. So it's total 3 instructions. So what is an instruction? It's a basic of basic operation, which means it's an atomic. Atomic means it cannot be divided into 2, or it cannot be stopped in the middle of the process. It should be done. The instruction, this one, each of them cannot be. However, the counter plus this operation need 3 operation. It can be interrupted in the middle. Okay. It can be interrupted. It can be the divide into divide by the instruction. So because of that, we have the synchronization problem. So this is the example of the, in case of 5, it's the same problem. So output is, in this case, if the 2 of the instruction of the counter plus is executed, and the next 2 is executed from the minus, then output is 4. It's the same example. So we will see the details of the such a race condition, and we will see how to solve the race condition. That is the synchronization. Okay. So first option is we can allow one process execute all transaction. Actually, this concept is called transaction. So transaction is a group of operation. It can be logically. We are going to consider group of operation as a atomic. Okay, logically. Physically, instruction is an atomic operation. But logically, so we will consider a group of operation as a transaction. So transaction, many of the operating systems use such a transaction as an atomic operation. Especially the database system use a lot as a transaction. That is the reason you never use the instruction level operation or whatever in the programming. Instead, transaction by transaction. My transaction is failed. My transaction is aborted. My transaction is successful. Something like that. Not my instruction. So, however, basically, we will consider group of data and group of instruction and by group of instruction. So, this is just assembly code. So, case 1, we can execute. So, without considering transaction. Okay, we are not going to consider transaction. Transaction is a very high level of the synchronization problem. The synchronization solution. So we will see later the transaction, but first we will see the 3 different cases. The first one is, why don't we execute the one by one? First instruction from the plus and next plus from the minus and take turn. So which means read the data from the memory, okay, fine, and read the data from the memory by the second process, and the +1, -1, and write the data, and write the data. So this is the same example as the previous bulletin board. Okay. Another option is we will start from the second process. In this case, the student B, output is the 6, as we have seen before. The third option is, why don't we execute the one process first, the next process, it will be the 5. Okay? So, to address that problem, first we are going to define the more details, the structure in process, which is called critical section segment of the code. Critical section means, so whenever a process needs to access the data that holds the race condition, which means it's a shared data and you update or write the data. Whenever a process needs to access the data that is shareable, also write the data with that holds the race condition, that the code is called the critical section. Okay. So what is a process? Process has a series of thread of instruction. Some of the instruction is just read the data, what that's it. And also it's only local variable, like the static object. Okay? But sometimes you need to access the data which is shared by other process, or you can also communicate with the other process at that time if that operation cause the race condition. In other words, synchronization problem, we will define such a code, group of code as a critical section. So we can define the process as this group. This is a critical section. So we have instruction. Among instruction, sometimes we need to access like read the register. For example, in the previous so this is a part of the instruction. This part calls the race condition. So we will define this as the critical section. Same thing, this part will be critical section of process 2. We regard the group of the instruction that calls the race condition as a critical section. So before a process enter critical section, that is called entry section. Okay, just before enter the critical section, that is called the entry section, and this one is exit section. So why do we need entry section and exit section? And critical section also. Why? Yes?
Well, if you're able to separate it out like that, you can run the entry sections asynchronously and then run the critical sections synchronously.
Think about going to bathroom with a key. Before you, so this is the critical section is your bathroom, toilet. Then to enter to use the toilet bowl, you need to get the key from desk or Professor Lee's office. Okay, that is the entry section. After you return to Professor Lee's office, you need to return the key. So to manage the lock, we are going to define entry section and exit section. And in the middle is the critical section. If we do not have any problem to access such a shared data, we don't have to define such a thing. But because of race condition, we define that any process that needs to access the shared data with the other process, that's called the critical section. And the after exit section is everything, it's just a remainder of the section. It's normal, okay? The instruction. So problem, one process has the structure of a process, and another process has the same. Any process has the same the structure. Critical section, and covered by the entry and exit section, and remainder section. Then our problem is how to define entry section and exit section. How to manage the key. What if we have two keys? Then that causes the problem. So some of the students are lined up in front of my office to go to the bathroom. I'm sorry to make the example of the bathroom, but one student is a really critical situation. Then we need to give the priority. And also, sometimes it can be first in, first out. But sometimes we can make the different rules. Okay? Only high priority can get the key. And when you return the key, you can return the key to the professor. Or you can return the key to this group of the process students who are waiting for the bathroom. Right? So depending on such rules, so it can be various different the synchronization problem solution. So we will see. Okay? From the very basic, from now on is more algorithm specific the approach. Okay? Eventually you are able to implement. The implementation itself is not very difficult. But this is a very simple the solution for the synchronization problem. What is a turn? Turn is kind of key. Who's turn? So let's say we have the process I and process J, two processes. We have only two students who are waiting for the bathroom. So process I has the critical section means the instruction that need to access the shareable data, shareable with other. Okay? When this process enter, check whether turn is global variable. Okay? So global variable turn is J1. What if turn is J? Which means it's used by other process. Process J is using the bathroom, is critical section. Which means it's a loop, infinite loop. Cannot enter critical section. Got it? Because it's true. So turn is J. Okay, assign. So it's true. So one is a for loop. Until when? We have process J, it's the same structure. One. Turn is what? I. Okay? Then critical section. Turn is J. I. Which means process J is done. Everything. Updating data, increasing data, whatever. Okay? Then once at this time, this is in loop forever. Cannot enter this one because it's always true. Then when process J is complete, critical section, this one is the exit section of process J. Turn is I. So this value is changed into I. Then what happened? What happened? This is the force. Because turn is changed into I by the exit section of process J. So this is a force. Force means you can get out of from while loop. So enter critical section. Okay. At this moment, processor J has another critical section part, which means it has a entry section code while. So check. This one is changed to I. Is it I? Yes, it's true. Which means the bathroom is used by the I. So it's a loop. Okay? Until process I is exit this critical section, then turn is changed to the J. So this is a true, a false. So then enter this one. Then, is there any critical section problem? Race condition? In case the race condition, yes, it's a race condition, but no synchronization issue because we are managing this one. This is the basic of the synchronization solution. In case of how many process? Only two process. Only two process case, you can use such a simple solution. Okay. So, first, when we are considering solution of the critical section problem, so we have the three requirements. The solution, not always they don't have to satisfy all the condition, but perfect solution satisfying with the three conditions. First, mutual exclusion. Mutual exclusion means how many students can use the bathroom at the same time? Only one, right? It's the same thing. Only one process can access the critical section. All the other process should wait. Okay? So that makes sense. That is the first thing. And that is a mutual exclusion. And progress means only process in the entry section which means those who are waiting for the bathroom in the queue. It can be queue, it doesn't matter. It doesn't have to be always queue. Those who are waiting for the bathroom, those students will decide, the next term. Not by Professor Lee, not by operating system. We are not going to use the rule or whatever. The process in the entry section will decide the next term. Okay. So some of the process we should to enter, which means the process in the entry section. Those process decide, the next process, by themselves. That is the progress, Then, third one, what if we decide that group of process who are waiting the critical section. So some of the process are waiting for the critical section, but when they decide, they always decide the process youngest one, youngest one first, not oldest one, youngest one first. So there might be a process who never got the chance. If that is old, still old. So that should not be the forever, which means bounded waiting. Eventually, process need to get the chance to enter critical section. Otherwise, sometimes there might be the process who never get the chance. That is called the starvation. So starvation is always a big problem in the operating system. One, because the operating system, main job of the operating system, coordinate the resource, limited resource. So if we have the unlimited resource, so like the shareable, whatever you want, you can share, you can write the data, you can do that. But because the operating system manage the limited resource, some condition, so they need to coordinate. How to coordinate? The condition is no starvation, which means the bounded waiting. That waiting should be bounded. Okay, so let's see the solution. Before that, we can classify such a solution by three. One is software solution. Software solution is, for example, this one. This is a software solution. Do we use any hardware? Do we? No. We use just a simple programming code. This is called the software solution. So software solution. But always it requires, because we need to use anyway, loop. Keep checking. The global variable or key value or something. So that is called the busy waiting. So always the software solution is simple to implement. Problem is always busy waiting. Busy waiting means it need, like this one. Each processor should have while loop. Sometimes it costs 100%, the CPU utilization, which means it's so bad. So there's no chance for the other process. So that is called a busy waiting. Hardware solution. What is the hardware? Instruction. So nowadays, always the company like the Intel or the semiconductor company, they try to make the CPU hardware that can process some of the instruction in their chip, not by errors. Why? Because such an instruction is the fastest way, most fastest way. So the most advanced, the CPU, the chip has more instruction. However, if you have a lot of instruction, it's also a problem. What kind of problem? Power consumption. It's a lot of heat and it's complicated. That is the reason register and the instruction, number of instruction and the space for the register are limited. Okay. So that is a hardware solution, mostly instruction and operating system. Okay. Operating system solution is in between software and hardware, using existing instruction the operating system has some additional data structure. So they try to use such a extension of the hardware solution, but add a little bit more system code. It's a software, okay? But operating system is separate as the operating system solution. So we will see the first, the software solution. It's called the algorithm 1 because it's just nothing but the naive way of the critical section problem. So this is a two-process case. So we have the process 0, like this one. It's almost the same as the first example, right? First example, we define the turn, either process I and J. Similarly, process 0 and process 1. It's the same, almost the same. So when they leave, you check whether this is my turn or not. So this is a process 0 case. So there is a global value of a turn. Turn is equal to 0 means, okay, so it should be 0. Turn is 0 means, so process 0 can enter the critical section because its turn is 0. Check whether turn is 0, not 0. It's a false. Because turn is 0, not 0 means false, right? Not 0 is a false. Then process 0 can enter critical section. It's the same idea as the previous one. But previous one we used instead of number we used I and J directly process name. But here it's a 0 or 1. Okay. At the same time we have process 1. It's the same thing. Turn, but however, while turn is not 1. That's the only difference. Then exit section is give the chance another process, process 1. Turn is equal to 1. Okay, then this one will be changed 1. Then if this one is a false, then enter the critical section. Before we check the requirement, we will see the step by step what will happen. So we have the two processes, process 0 and process 1. First, turn is 0. Okay? So initially set as 0. Then P0 would like to enter critical section here. Okay? The entry section. So then entry section, check whether turn is not 0. Which means if that is a false, then enter critical section. Okay? So it's a false, that means it's an exit while loop, enter critical section. At the same time, this time, the P1 would like to enter critical section. And check turn is 1, it's not 1. It's a true. Because the turn is 0, so not 1 is the true. True means it's a while loop. So P1 cannot enter critical section. So P1 is waiting. It's a busy waiting. And when P0 is complete the critical section, then it's exit. So when each process exit, change the value of the turn. Then once this one is changed and the P1 is checking the turn is 1 is false, not 1 is false, then finally enter critical section. Okay? Then check the requirement. Mutual exclusion, how many processes at the same time? Only one, at most one process can enter critical section. Who decides the turn? What is the progress? Progress means only process in entry section, those who are waiting in that room, decide the next turn. Okay, but here, who decides the next turn? Process in the exit section. Who are exit? I'm done. I complete my job in the bathroom. Then give the key who one. Okay? Right? So sometimes that's not fair, depending on how to decide the next one. In this case, it's a two-process case. So there may be no problem, because either me or other process. It looks like a fine, but when we have the many processes, so only some of the process or one process can get the key only. So progress is not so good. Only two process case is okay, but the other is not so good. So eventually, some of the processes may wait forever, right? So bounded waiting. So well in case of two process case, but not perfect. Okay, so that is the algorithm one. So to address that problem a little bit, this is the second algorithm. You will see why it's called the algorithm 1 and algorithm 2, because it's not used in real life system. It's just basic idea. So we are going to define, instead of the key, okay, we are going to manage the flag. Flag, so this is a two process case. We are going to extend the multiple process later, but this is a two process case. Flag 0 for the process 0. So we have the banner check. Like if we are using airplane, when you go to the bathroom, there's always a sign, right? So use, not use. So green or red. So similarly, for each process, this is a process 0, process 1. It's a true means using bathroom. The first one, the process 0 is using critical section. False means not using. So we are, instead of key, we are going to manage the such a status of the data structure. That's called the flag. So initially, it's set as a false, nobody used. Okay, nobody used. However, if process 0 is using critical section, it will be changing as a use. Okay. So first, this is a process I case. We can have process J also. So same, when process I entered the critical section, so flag I is changing. Actually, this one is not using. This one is intention. Whether or not this process is in the entry section. We try to find which process are in the entry section. So flag I is changed true. Flag I is changed true. So process I would like to enter critical section. Check whether the other process are using the in the entry section. So if this is a false, then you can enter. There might be no problem, right? However, if this one is true, you need to wait. Okay? You cannot enter the critical section. Then once you exit the critical section, change my status. I'm not going to decide who is the next one. Okay? The previous algorithm, we give the key to other. But in this case, we just change my status. I'm not interested in the critical section one. So false. It will be changed the false. Then, if other process would like to enter the critical section, flag J is changing the true, then check flag I, other process flag. So it's a change in the false. Then this one can enter critical section. That is the difference. The first algorithm used the key, one value. Okay? But this one is for each process, we will check the status. So, first, why don't we see the step by step, then we'll check the requirement. Process 0, first, false, which means nobody waiting for the critical section. Nobody, no student, no process are waiting the critical section. Then process 0 would like to enter critical section. Okay, which means it's a change into true. So you announce, I'd like to enter critical section. Then check the other process, process 1, process J. So then is false. False means you can enter. Nobody no process are interested to enter critical section. Then enter critical section. At that time, flag 0 is true because it's changed. It's still 1 is still false. At that time, when process 0 in the critical section, if process 1 would like to enter critical section, change the flag true, which means process 1 would like to enter critical section, and check the flag of process 0 is true. True means waiting, waiting, waiting. Until this one is process 1 is completed. So by changing the flag, so it will enter process 1 enter critical section. Okay? Mutual exclusion, only one process can enter the critical section. And what about the progress? Who determines? Even though this time, even though this does not specify the next term, okay? Because of this one, because of the flag, because this flag will be checked by another process, okay? Which means this one directly, not like the first algorithm, but still this exit process affect the decision of the next one. So it's not the perfect in case of the process. Bounded time, it depends on this one. Why? And also it's not the better than algorithm one in case, what if flag 0 is true, flag 1 is true as an initial. Both of them are true as an initial. Process 0 would like to enter is true, and flag 1 is also true. It cannot enter the critical section. And this one is also true. But process 0, flag 0 is true, so no process can enter critical section in case both of them are true. So bounded time we cannot measure. It's not. So sometimes it may be forever. Okay. So algorithm 2 can be easily extended to the process 0, process 1, process 2, and using the flag, but it's still not perfect. So kind of process algorithm 1 use the key lock, okay, and algorithm 2 use status of each process. So next one is, why don't we consider both of them together? We manage the key as well as the status of each process. That is the turn, okay? One is the turn, it's a key. Another one is the flag for the status for each process. So this is the structure of the synchronized process. So we have the entry section, critical section, and exit section. Entry section, we have the turn. This is a process I. Okay, we change the turn into the J. Okay, and flag. I try to enter the critical section. Okay, then we will check flag J. Flag J is true or false, and turn is J. Whether J is using this one. What does that mean? How can you exit the while loop? This should be false, right? In case of false, you can enter critical section. This is an end. End means either this one is a false or either this one is a false. Which means either J is not in critical section. Okay? Not intended even. So not in the critical section. Or flag J. Flag J means so other process not intending to enter the critical section. At that time, you can enter the critical section. So let's see the step by step. So as a default, we have the turn is equal to 0, and flag is both of them are false. Then process 0, first the process would like to enter the critical section. I think this should be I. That makes sense. Flag I is a true and turn is I. Okay, let's see. So turn is a no. Turn is a G. Okay, so first turn is a 0 and flag is both of them are false. Then the process 0 would like to enter critical section. That means the flag, the status of the process 0, change it into true. Okay. Then turn is 1. Okay. Turn is, this is a false. Turn is 1. Okay. Then check the whether flag 1. Flag 1 is in this case a false. And turn is 1, 1. This is a true, but it's an end condition. So this is to be false. If either of them is false, then enter the critical section. So can enter the critical section. At that time, the variable turn is changed to 1, and flag information, the 0 is a false and true, and flag 1 is not entering the critical section yet. Okay, false. At that time, P1 is executed and would like to enter the critical section. Then that means flag 1 is changed into true, and turn is changed to 0. Okay. Then give, because I'd like to enter the critical section. Okay. Turn is changed to 0. So check whether flag 0 is 0 or not. True or false. Flag 0 is true because it's in the critical section. And turn is, I give the chance to other process. Turn is other processes is true. Both of them are true. Okay, so it cannot enter critical section. Then how can it enter the critical section? In other words, when this is a false, in case process 0 is exit, this one, when this one is exit, flag 0 is changed to 0. Okay? 0. So this is a false. Okay? Then enter the critical section. So this is a, you can avoid the problem of the both, even though these both of them are false, because of turn, you can decide the next turn. So in algorithm 2, if we are using the only flag, in case both of them are true, you cannot enter. None of the process can enter critical section. Okay? There's no chance to change because in the exit section you can change the status of the flag. But if you combine flag with the turn key, okay, by changing the key, you can decide the next process to enter critical section. Okay? So check the requirement. What about the mutual exclusion? Only one process can enter the critical section. Okay? Only one process can enter critical section. Definitely, this is a mutual exclusion. Okay, then what about the progress and bounded waiting? If a processor not intending the critical section, which means here this one is not, it's still false. When a process leave, just change the fault. Then because of turn, at that time, because of the turn, if you have the multiple process, the turn will give the chance to other process. So not only just a flag is I'm not interested, but because of a turn you can decide the next one. You can change the turn in the entry section. So which means the process in the entry section can decide the next process to enter the critical section. So this, and also this one, it's not forever because we have the turn. In case of both of the flag, it's a true, but because of a turn, it can be decided the next one. So bounded waiting will be solve the problem. So this is called Pearson solution. So Pearson solution is the first simple the solution for the critical section problem. It's practically used? No. It's too simple. It's a software based. As you can see, it has a lot of the busy waiting. So because of the busy waiting, it's not used practically, but to understand the basic or the comparison. You can compare the performance of the new algorithm with the Pearson solution. So this is the software-based synchronization solution. Next, hardware. Hardware, we can use the instruction or any hardware operation. So such as interrupt. Okay. So interrupt, what is an interrupt? Interrupt is the communication method between the processor and between the hardware and the operating system. So what happens if you disable the interrupt? You can keep doing your job. It's kind of loud. Okay? If you disable the interrupt, the operating system will not allow any communication between device or the process. So it will be kind of a stop the current status. So which means the process that requires to disable the interrupt can enter the critical section, then do the any modifying or the accessing the shareable data. Then once it is completed and enable the interrupt, which means other process can the request disable the interrupt. So it's kind of a lot. So this is a basic idea of the synchronization using hardware. So we can define such a process as the acquire the lock and release the lock between the critical section. Okay. So first instruction is a test and set. This is an instruction. Okay, which means it cannot be interrupted. It cannot be divided into, or it cannot be stopped in the middle of the process. So how does it work? Test and set. Input is true or false, Boolean value. Then this input is saved. Okay, saved in the RV temporary space, and always change it. The input value is the true. Okay. Then return code is the same as the input. Test, just the test. What is my value? What is the input value? In case input is true, output is true. In case input is false, output is false. But what about the input value itself? It is always changed to the true. Set as true. That is called the test and set the instruction. This instruction is cannot be divisible. Okay. So for example, why don't we consider input as a lock? Lock is false, which means it's not used anyone. Okay. If you call this instruction, if you execute this instruction with a lock, output is what? Same. Okay. Output is the same as input. So output is false. However, lock value itself is changed to the true. Okay. So this is a test sensor. How can we use this test sensor? Here. So entry section and exit section. So when you enter the critical section, you can execute the test sensor. Test sensor, if log is a false, okay? Log is a false, what is the output of this one? Same as the input value. Input is a false, this is a false. Okay? So what is, you can exit while loop, which means this process can enter critical section. At this time, log is true. What about other process? Other process has the same entry section and exit section. Check, test, and set, and log. This is a true. Output is the same as the input. So this one is a true. So 1 is a true. So you cannot enter critical section. So keep waiting. Okay? Keep waiting until this one exit the critical section. Log is a false. So when log is a false, this is a false. So if you test and set, this process test and set, this output is the same false. Then value itself log is also changed as the true again, which means I'm using one process using critical section. So the other process cannot enter the critical section. This is a hardware solution using instruction, test and set. Another example of using the hardware solution is a swap. What is a swap operation in general? Change the value, swap the value. So it's the same thing. Input is a 2, A and B. Okay? It's a void. There's no output. It's just a change the value. Okay? So it needs, I think the 3 instructions may be enough with the temporary space. Okay? So, for example, if this one is a key and this is the log, and this is a, for example, true, and this is a false, I'd like to want to access a critical section and log is not used. Then change. I will give my ticket. Okay. Then log is I can enter the critical section. So output, no output, but just change it, log and key. How can we use the swap operation to solve the critical section problem? So first, the key is true, which means I am right to enter critical section. So it's the intention. Then check key is true. Okay. Then if key is true, if yourself is entering the critical section, and swap with this one. If key log is false and key is true, which means after you execute the swap, log will be true and key will be false. So if you go to this, key is true, no, key is false. So this operation is false. So false means you can enter critical section. Once this process in the critical section, log is true. So if other process would like to enter the critical section, run the same thing. Then at that time, check the swap, log and key. This is a true because it's currently used by this process. And the key is also true because when this process enters the critical section, the entry section is set as a true. Even though you swap true by true, it's still true, right? Even though this is a while loop, during the while loop, key is true, it's still true. So keep checking, keep checking, keep checking. Until when? When this process exits the critical section, which means log is false. Log is false, this is false, and when you swap, so key is false and log is true, So going to this check, key is not true, so which means false. So enter the critical section. So you can use the swap the operation. Most of the processor, CPU, provides such a very well-known instruction in their chip as an instruction. So we can use such a hardware solution. Okay? However, this is the same problem as the previous one, at the algorithm 1. Okay? Algorithm 1 has the problem of the progress and bounded weighting. It only provides perfect mutual exclusion. So it has the same problem. So can we change, modify? This is the, so far it's very straightforward. So you can, when you see the algorithm, you can easily understand. But from now on, it's a little bit more complicated. So we try to revise such a swap. We try to use a swap and the test and set for the synchronization solution that can satisfy with the 3 conditions. So mutual exclusion and mostly the progress and the bounded weighting. So this time, when a process enters the critical section, this is a critical section. So this is the entry section, and this is the exit section. So entry section, I'm waiting. First, we are going to manage the flag. So that is waiting. I'm waiting. I'm announcing, broadcasting. I'd like to enter the critical section. I'm in the entry section. I'm waiting for the bathroom. So that is true for this process. And key is true. Okay? Key is the same as in the Peterson solution. So we'd like to use the key. Why? Why? Because all processes are true in the waiting. So we need the key to break one of them. So it's a true. Okay, then check. 2 things is from the Peterson solution. So waiting is a true, and key is a true. In case true and true, you cannot, first time, you cannot enter the critical section. Okay? We need to check the log value. Okay? If log first is a false, nobody use the bathroom yet, critical section yet, which means run the test and set. Test and set, so we return the same value as the log, which means key is false. Key is false. Then the log itself changed as the true. So this one is changed as the true. Then do the while condition again. At this time, waiting is still true. Okay? It's still waiting, and but key is set as the false. So, which means this one is a false. You can exit the while loop, which means you can enter the critical section. When you enter the critical section, I'm not waiting more because I'm in the bathroom, right? So you can change it. This one is the false. Okay? Then enter the critical section. At this time, if other process would like to enter the critical section, which means waiting J is true and key is equal to true, and Y. Waiting, currently waiting is a true and key is a true, which means I need to execute this one. The key, test and set, log. Currently log is a true. So output is still true. Right? Then this is a true. So still true, 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 true. Until when? Until this one is current process exit the critical section. which means log is force, then it can enter. It may have a chance actually. We will see why. Okay? It may have the enter. If we do not have this part, it's the same problem as the Pearson solution. It can still affect the next term. Okay, so may have a chance to enter when the log is force. Then see what happens when current process is exit. This one is different from the other. What is this? It's a modular. Modular is the remainder. Okay? So we'd like to decide who is the next using this. Even though it is executed by this process, but this process does not decide the next one. It's always I will give the chance for the next line. Okay, it looks similar as the first come first serve. It's not first come first serve, but next sequentially give the chance. Okay, sometimes next one may not have. So for example, in this case, the other process plus 1 if n is the total number of process. In case the plus 1, the j is the last one, it will go back to the beginning. Okay, that is the reason it's use the modular. Okay, then if j is not I, which means there are 2 or more processes. If you have only one process, it's always the same process. J and I are the same. Because it's one process, next of this one, because of the modular round 1, it's still same value. If not, okay, so, and waiting, not waiting j, which means to just skip the value of not waiting, because we don't have to give the chance to the next one. So we have the process 0, process 1, process 2, process 3. Process 1 is currently the critical section. Then we would like to exit to give the chance to the next one. However, if the next one, process 1 is not waiting, we need to skip to the next one until true. So that is this one. Okay? So this is a force, change the force, true, force, true. And skip, and this process will get the chance. Then waiting. If j and I is the same, which means all process is a force. So go back to this one, okay? Which means no process will get the chance to enter because nobody wants. There's no process in the entry section. So which means just release the log as a force. Okay? Then after we decide that this is a true, process 3 is to get the chance, which means we change the waiting is a force of that process. That process waiting, why don't you check this one? Waiting I is a force, right? So it can enter the critical section. Okay? So again, we have the waiting. Waiting is expressing I'm in the entry section. Key to break down the waiting is the truth. Okay? And in the while, we will use the past and set. So this is the same as the past and set here. However, we are going to check whether waiting of the process and the key of this, if either of them is first, can enter the critical section. How can we get this one? So because in case of log is a force, then directly enter. Otherwise, other process who are in the critical section give the exit when the other process in the critical section exit. When the process is exit, it will determine the next one using this algorithm. Okay, next, until who is waiting for the critical section. Then, when once that the chance is the exit, the wait is the false. Okay? Then the critical section. When the process is exiting the critical section, so give the chance to the sequential circular path. If this is the current one, next, until waiting is true. That is this algorithm. Okay? What about the mutual exclusion? Yes, only one process can enter the critical section. What about the progress? Among, what does that mean, true? True means the exit section, right? And the entry section. True process, true of waiting means there is a process in the entry section. Then, how can we determine the next process? Sequential pattern. It's a sequentially. Yeah. If a process, this one is a true, and current one, it will be set as false. False, true, then next to this one. Next time, when this one is exit, process 4 will be selected. And next, what if it's the last process, go back to the beginning. Okay, it's a circular pattern. Okay, then what about the bounded waiting? It's a maximum 1 cycle. Number of n times. Eventually, process will get the chance to enter critical section. So, bounded waiting, the mutual exclusion is okay, and the progress, the only among the process in the entry section will determine. And this waiting is not permanent, infinite. At most, the worst case is 1 round of the process, which means the n number of the process turn eventually will get the chance to enter critical section. Okay, so that is the mutual exclusion, progress, and the bounded waiting. Okay, so that is the hardware solution. We use the test and set and the swap instruction. The last one is operating system. The operating system solution. Quickly, within 2 minutes. I'm going to borrow 1 more minute. Okay, so there is the data structure provided by the operating system. What about the queue? Who provides the queue data structure? It's a hardware solution? No, it's a data structure provided by operating. Most of the operating system provide. Even the programming language itself provides such a data structure, like the Java provide the array or list or some generic class. Similarly, operating system, most of the operating system provide such a data structure. One of them is the semaphore. What is a semaphore data structure? I don't think you learned in your undergraduate data structure course the semaphore, but semaphore has the integer variable. Okay, then you can access the semaphore plus or minus the value. Okay, so which means so you can wait and signal. Wait is increase the value and signal is decrease the value. So there are 2 operations. And the value is increased and decreased by such 2 operations. So wait S is the decrease and signal is the increased value. Okay, 2 operation and integer value is managed. Then what if we limit such an integer variable by 1, which means 0 or 1? That will be log. Okay, acquire the log. That is 1. Signal is 1 and wait is 0. So if we limit the integer variable 0 or 1, it's a kind of a log, which is called mutex. So mutex is the semaphore. It's a specialized semaphore limited by the 0 or 1. It's kind of lucky. How can you set the lock? Signal. Signal is to set the lock. Release the lock is a wait. So using this one, because it can be worked as a lock, we can solve the problem of the critical section. Okay? So that is called the mutex lock. So that is the reason when you use the Windows 95 or the 98, from time to time there is a pop-up mutex lock problem. Mutex lock problem is mostly happen in the synchronization problem because the operating system cannot handle such a problem. So we will see one. Sometimes mutex lock will be happen in the next class. So that is the end of the operating system solution. Then I will